We are going to start with this finite difference representation for the advection equation. And the one we are going to present here is called explicit forward time centered space method. Sometimes it's also written as FTCS method. FTCS method. So here this is the equation. And first we are going to find a finite difference representation for the partial derivative of u with respect to x, and another one for the partial derivative of u with respect to time. And so first we are going to start with the partial derivative of u with respect to x, and we're going to find here, we're going to use here in this method a second order representation, but still using only quantities known at time j. So basically here we're going to consider two Taylor expansions. Both these expansions are done around n and j positions. So these are this point in our two-dimensional mass. So as you can see here, everything, all the derivatives are here are calculated at this point in order to find an approximation for the u function at point n plus 1 and time j, and on one case, and on the other hand, the other Taylor expansion is to find an approximation for the u function evaluated at point n minus 1 and time j. So as you can see here, the Taylor expansion is done up to second order in the delta x, so that the error here is of the order delta x to the cube. And as our aim here is to have an approximation for, find a different approximation for the partial derivative of u with respect to x, so that we don't want it to appear, the second order derivative we don't want to appear. So we have to make a combination of the two so that we are keeping this term, but we are eliminating the second order on delta x to cube. So in order to do that, basically what you have to do is the first equation minus the other. If we are doing that, basically what you have is the following. Then you have this one minus this one, so basically u evaluated at n plus 1 at time j minus u evaluated at n minus 1 at time j. It's equal to 2 times this one, because these two they simplify each other when you are making one minus the other. 2 times the partial derivative of u with respect to x evaluated at point nj times delta x, plus this one also disappears, so that the other order of the remaining one and the first the remaining term goes as delta x to cube. So if we clear from here, we clear this the finite difference representation for the partial derivative of u with respect to x. That's the result that we have, and as you can see here, it's a second order representation here for the partial derivative of u with respect to x. So this is the one that we already have gotten for one of the terms in the equation. And now we are going for the other one, for the partial derivative of u with respect to the time. And here we're going to consider a first order representation for that. So that's what's considered in this finite difference method here. So basically we are doing the same thing as we did in the forward Euler method. So here we are going to just consider one Taylor expansion around point nj in order to have an approximation for the function at point n and time j plus 1. So this is the Taylor expansion that we do have. So here, as you can see here, it arises a partial derivative of u with respect to time evaluated at point nj times delta time, and next time is of the order of delta t to the square of the delta t. So again, if we clear from here this an expression for this one, that's easy to do, and the result that we have is this finite difference representation, and the as you can see is the order of the representation is delta t. So combining this one and the one we have gotten before for the partial of u with respect to x, that's the expression we have. And from here, remember that our aim was to get, once we know at certain j, the value of the u function at different positions at certain j time, our aim will be to have the value of the u function at the next time step. Therefore, our aim will be to have an expression for this, this term here. So what we are going to do is we are going to clear from this equation this expression here, and if we are doing that, this is the finite difference representation that we have for this method, corresponding to the advection equation. Basically, the one we're getting is the following. The value of the u function at point n, and it's evaluated at time j plus 1. It's equal to the value to the u function evaluated at point n and time j plus this constant here, which is the c constant arising in the advection equation, time step over 2 times delta x, and it's multiplying the u function evaluated at n plus 1 and time j minus the u function evaluated at point n, sorry, this is n minus 1 here, n minus 1 here, and minus 1 and time j. And so, and this equation here, it's valid for the n running from 1 to n minus 1. So this n will run from, and the equations that we need in order to have the values of the u function either at 0 and at n capital N, which are actually the two boundaries, are the boundary conditions. So the boundary conditions are the extra conditions that are needed in order to have the values for the u0 at any j and the un at any jen, sorry. So here this forward time centered space representation is an explicit scheme here where this function here, in order to have the value of this function for each n, that can be calculated explicitly using this representation we have derived here, using just quantities that are already known, because here you can see that the quantities already known because they were calculated, it corresponds to the previous time steps. So just knowing the values of the u functions in the previous time step, you're able to get the value of the u function at the next time step. Now later we'll see another schemes which can be called, we'll call implicit schemes, that these schemes will require us to solve like implicit equations in order to get these the u functions at the next step, but we'll see it later. And here again, this algorithm is also an example of a single level scheme. That's why it's because only values at time j, yes, values at time j are needed or have to be stored in order to find the values at time j plus 1. So just one time, one step before the values of the u function, at one step before the ones that are needed in order to have the u functions at a certain time step. So on the other hand, here we have like a graphical presentation of this method. This is like the dashed line is connecting these 2 points here. That would be like this point. This is the open point, will be the unknown value of the u function evaluated at time at position n and at time step j plus 1. So time is running in this direction, and this is the this is the solid points here. The solid dots here are will be like the known functions, known values of the u function evaluated in this case at position n, because the x position is running in this direction, but at the previous time step, at time step j. So this dashed line is connecting these 2 points, and these 2 points are connected in the finite representation we have obtained for the partial derivative of u with respect to time. And on the other hand, this solid line here, which is connecting these 2 u functions here, and actually the u function here on the left corresponds to the u function evaluated at position n minus 1 and time j, and the one on the right we have the u function evaluated at position n plus 1 at time j. So these are the solid line representing the points that are connected in the finite representation method that we have considered in this FTCS method for the partial derivative of u with respect to x. As you can see here, so the time here, the partial derivative of u with respect to time here, is centered with respect to these 2 points, which are the ones that are connected in the partial derivative of u with respect to x. That's why this method is called this time-centered space method. Even though for that actually it requires to have like a different order in the representation for the partial derivative of u with respect to time and the partial derivative of u with respect to x. So basically here we have derived, therefore, our first finite difference method for the advection equation, and this is the one we have in this pink square highlighted here.